Welcome back, everybody. Today we're going to talk about non-condensables and what that looks like in your refrigerant circuit when you hook up your gauges, when you see those pressures moving around and things just don't make sense, when you check your superheat and your subcool levels and those values just don't stay consistent. They keep moving around. How do I determine if that's a bad expansion valve or metering device? Is there something else going on? Is it maybe my compressor, or is there something wrong with maybe the refrigerant itself that's moving through the system? Stay tuned. We're going to explain how and show you what to do. The reason why we're taking this video is because we have the ability to show you what non-condensables look like. If you look at the manifolds, you'll see that the top left-hand corner of the gauge is displaying 126, 125 psi, and the top right-hand corner is displaying about 315, 316 psi. And if you look down below, you can see our subcool and our superheat. And now what we have here is these numbers are fluctuating. When these numbers fluctuate, we have to determine, is it a metering issue? Is my expansion valve opening and closing, or is there non-condensables in my system? And the only way to determine which one it is to understand that superheat and subcool do not fluctuate in this direction. I'm going to go over this in a lecture here in a little bit so I can explain what it is that you need to understand for that to be clearly understood. The suction pressure and head pressure are not enough information to determine if it's a valve. It's not enough information to determine if it's non-condensables. The superheat and the subcool aren't even enough information if they're fluctuating. You're going to need all four of these values present to understand this diagnostic. For example, if you look at the top right where my head pressure is going down, well, when the head pressure goes down, the subcool goes down. So that kind of lines up a little bit. But if you look at the other side, my superheat was not adding up to a proper correspondence. Meaning if I had a low subcool, I'm generally not going to have a low superheat in conjunction with that. And if I had a high subcool, right, and my superheat was dropping, well, that would kind of make sense if it stayed in that direction. But when it's fluctuating up and down, that's when the numbers just don't add up. The numbers should never constantly move. Now, your subcool, if you had a bad valve, you would have a high subcool, you would have a high subcool and a high superheat. If you had an overcharged system, you would have a high subcool and a low superheat. If I had an undercharged system, I would have a low subcool and a high superheat. So when my superheat and subcool are moving constantly up and down, and we start getting a different combination that are different from those three that I just talked about, then it doesn't make sense. And if it doesn't make sense, it's because your data that you're going off of is not accurate enough, and a valve will not give you wrong data. What will give you wrong data is non-condensables, which could be moisture, it could be air, it could be anything that was introduced to the system during the installation, or if not during the installation, maybe during services. Right? People not putting their gauges on properly and purging those hoses out. They could easily add other refrigerants to it by 1 ounce at a time, or even some moisture. And so once those integrate into the system and the compressors moving that gas with those non-condensables, then we're going to get wacky pressures and wacky superheat values and subcool values that we can never compute. And so I want to show that to you because we do see it in our industry, but it's not that common. And the fact that it is present on this unit that we're looking at it's a perfect example for us to show you also what it will take to fix that. So the steps that we would need to fix this unit would be to recover all the refrigerant. Once all the refrigerant is recovered, we would need to remove the dryer. After the dryer is removed, we'll need to install a new dryer and then pull a proper evacuation down to 500 microns. You want to make sure that you're not pulling your vacuum too fast or using a high CFM vacuum pump, and freezing any moisture. We want to make sure that we're pulling a good, slow, steady vacuum, get down to the proper microns, and then we want to weigh in a factory virgin refrigerant charge that we know it came out of a bottle that has never been tampered with. Now, there's a value on the unit that will tell us how much that needs to be, and there's tools that we need to use to help us get that amount in there. They're called scales. There's also torches that are involved. There's recovery tanks. During the recovery process, we want to speed that up, so we may need a cooler with some ice or some water, in addition with a sub cooler, which is an additional coil that we can move that gas and expedite that. However you decide to do it, whether you want to take all day to do it, half a day, or you want to get it done as fast as possible within a timely manner for efficiency purposes, it requires tools, technique, skills, experience, and that's not going to come at the lowest price in town. And if it does, maybe a step is being skipped. So I want to go ahead and just show you on camera what kind of tools we are talking about. If you look here, I'm going to go ahead and pan out. You can see that we have our recovery machine over here, our virgin refrigerant 410A tank, a recovery tank. We have our torches, a nitrogen bottle. Okay, I don't have the nitrogen regulator for this video, but we'll need that to get nitrogen out of there. I do have a cooler that we can put some ice and water in. This is a sub cooler that I was talking about. We have our 3 CFM vacuum pump, so we can get a long vacuum. We have a brand new biflow refrigerant dryer that you want to use if it's a heat pump. And we have a set of scales so we can scale in our refrigerant. Now, if we were to look at how we have these gauges set up, you can see that we have everything clamped. And those clamps are not on any type of couplings or anything like that are going to hinder getting a good reading. You can see the solder joint and the clamp is just past that. So we're getting a good accurate value. If we look over here, we can see that this unit here is a 410A and it holds 11 pounds, 12 ounces, plus the refrigerant line set. So we're definitely more than 12 pounds on this. And with that, it's important to scale in this refrigerant, and then we can balance the superheat and subcools past that. But if you're wondering what tools you would need just to do this job and put that dryer in there, it's quite a bit. Now, this doesn't, you also need the gauges and then low loss spinning hoses and everything else. And there's other tools like hand tools that we're not putting into the equation. But this is a big job. And this job is not something to take lightly because you want to make sure that you're using proper industry techniques. We're going to go ahead and take it to the smart board right now so we can give a lecture on this. Hope this video helps you out if you're trying to diagnose what superheat and subcool value should be when we're dealing with non-condensables. And if we look here, we can clearly see that head pressure and suction pressure and that superheat and that subcool are constantly fluctuating, and we are not going to obtain an accurate diagnostic if this system needs refrigerant, if it doesn't need refrigerant. If we do have an issue with a valve afterwards, we're going to have to rely on first putting new virgin refrigerant in there. Now, with my experience level, I'm telling you that we don't have a bad valve. This is just purely, we are moving other things beyond just 410A in this system. And stay tuned. Okay, getting right into the lecture part of this, we took you to an actual unit that was performing that way. We showed you through that video what tools to use and what we would have to do to actually fix that. That's pretty neat. A lot of customers don't realize what all is involved there. Some technicians don't even realize what all they have to build into um, their buildup when they're explaining to the customer like what's involved with just removing gas and putting new gas back in. It's not just a simple process. So, if you need to take this video and show them, maybe a part of the video and just explain, hey, look, this is what all I need to even get this job done, to do this job the right way. Or if you're in the industry, you just haven't received, this many tools and that level of responsibility, it's just something to look forward to when you get there. Behind me, I just have a quick snapshot of those same gauges on that unit, just to kind of show you. If we just looked at a quick glance, that doesn't look bad. I'm going to go ahead and highlight a couple things that I would first look at as an indicator, as if my subcool had a value on the unit that said, hey, 8 degrees, I may not be able to achieve that number. 6.2 is not too bad. That just guarantees me, yeah, I've got liquid refrigerant leaving that condenser. Over here, this is everything that's going on my evaporator. I'm returning back a vapor because I'm returning back 15 degrees. That number is the difference between my line temperature and my saturation temperature. Saturation temperature is 55 degrees. So that coil is, 39 degrees. So the coil is not freezing. The coil's not too warm. The suction line temperature isn't too warm. It's not too cold. It's 55. The distance between these two numbers is 15. And that's the range that I'm looking for. We want to be between that 12 and 18. If we're outside of those ranges, it's not terrible, right? As long as we're not like 28, 30, 25, or if we're maybe 10 or 5 or 0 or a negative number, that would be horrible. So we have vapor returning. We guaranteed that. We have subcool returning. But the problem is these numbers aren't consistent. So if they're not consistent, then there's something else in the system that's causing that. And we want to know, is it a compressor that's causing that? Is it how do I know if my compressor is good or my compressor is bad? Very simple. We'll go ahead and just look at this real quick. If we were to just look at the 117 and the 302 head pressure and suction pressure, how many times can this number go inside of that number? If we were just to divide, those into each other, what would our pumping ratio be? I'm just going to do it real quick. And that comes up to 2.58. So I'm going to write that up here, 2.58. And that's our pumping ratio. That's a pretty solid pumping ratio. Now, in that video, we saw that this number got up to about 125, and we saw this number got up to around 320. And even if we looked at those numbers at their higher value, let's just say 320, divide that by 125, we still come up with 2.56 pumping ratio. So our pumping ratio on our compressor is good. There's no concerns there. That's just a quick rule of thumb. If you have a good pumping ratio, what's next? So typically when we're diagnosing, we can't just go off of pressures, because the only thing I'm really going to get out of that is a pumping ratio. Or am I close enough to the values that I would normally see if this system was working properly? Meaning, is my evaporator coil above 34 degrees? Well, if I am, I'm going to be 100 plus. If my condenser is, above, 85 degrees on my, discharge temperature, of course I'm going to be, two high 2s, 3s, mid 3s right in there. And that just kind of just tells me that, hey, okay, everything in this looks fine there. That pumping ratio looks good. The next thing I would be looking at is my subcool value. How close is that to what the factory charge is supposed to be? And then I would look at that superheat to see if I'm flooding my evaporator coil out with too much liquid, or am I do I have too high of a superheat, meaning that I'm not getting enough liquid to
my evaporator coil. So when you look at this at a quick glance, everything checks out. But if you look at that video tells a different story. Just to get on to the next page here, I understand that you're in the trade. You may know this already, but just take a second, okay? We have four key components here. We have a condenser, a compressor, an expansion valve, and an evaporator. Let's don't forget what these things do. The condenser, it rejects heat. It condenses gas to a liquid, and it provides a liquid state, which is your subcool. That's it. Okay. Um, let's look at that compressor. That next thing, it moves gas and it gives you a pressure rise. I put these dotted lines here to separate low from high because that is a critical component. So these are all key components, but we have two critical components: the compressor and the metering device, the TXV. And so here we're a gas state. Here we're a liquid state. Um, High side, low side again. High PSI, low PSI. We're moving high PSI and low PSI in liquid, high PSI, low PSI gas. Here we're metering liquid and we get a pressure fall. So here we have our pressure rise. Here we have our pressure fall. So we're high pressure here. Over here we're low pressure. That evaporator coil, it absorbs heat. Don't forget that. It evaporates liquid, right? In a sealed system, and it provides gas, a gas state, which is superheat, back to the compressor. And so, we're moving not in this direct order, but high side, right? And then low side, back to the compressor. And so when we see these values, when we see numbers moving around, I can't take a high PSI and a low PSI and then look at my superheat over here, my subcool over here, and say that I have a bad critical component when my pumping ratio is solid and the valve, it's not, you don't even have the values moving in the right direction. We have a superheat subcool video that I want you to check out if you haven't done so already that clearly expresses that using a cup analogy. And then let's just get on to, if you were to look at the video again, I'm just going to let you watch that and just leave this up here just to explain, these four things. Pressures are moving up and down. Your subcool, it moves up and down. Your superheat, it moves up and down. And they never do they compute. When you're in that situation, okay, when you're in that situation, you have non-condensables, and there's only one way to fix that, and that's to start all over again with new refrigerant, a nice dry circuit, new dryers, everything. And just at a quick glance here, what we're looking at for them to compute properly, that would be if we had a high superheat and a high subcool. We know that's a restriction. Either your dryer's restricted, you got a kink somewhere in the liquid line, or you have the wrong size metering device or a bad metering device. That's as simple as that. The high superheat and low in combination with a low subcool would be low on charge, right? Our evaporator coil's starving for refrigerant. We don't have much subcool either. So those are two very simple things: low subcool, high superheat. That's low on charge. If our superheat was low and our subcool was high, that would be overcharged because that would be in conjunction. We're flooding the evaporator coil out with too much liquid refrigerant, which is coming from being overcharged and having too much refrigerant in the system. If there's anything else wrong, or if there's anything else other than these three, then the data that you're getting is wrong, and you're not going to be able to take that data and just make a correction by adding gas or taking gas away or removing the metering device and putting another one in there. It's wrong for a reason. So if you have good pumping ratio, if the pumping ratio is good, okay, and your pressures are moving up and down, and you have subcools and superheats that are moving up and down, and you just can't get anything to compute, then you have non-condensables in there. How do these non-condensables get in there? We hook our gauges up to these units. When we hook our gauges up, You may have gone from an R22 unit, now you're working on a 410A unit, and maybe your last call is an R32 or 454B. We're constantly in high temp refrigerant markets. It's not one type of refrigerant like it used to be a long time ago. There's now your entire day's route. You can work on 4, maybe 5, or even 6 different high temp refrigerants, and those are still left in your hoses. If you're not purging your hoses correctly, you're going to be introducing these different blends, and it's not going to condense properly or evaporate properly because it wasn't designed to do that. Also, there can just be air in your lines that when you're hooking them up, these hoses up to them, and you're not purging them properly with the refrigerants in the system, you could be introducing that air and moisture to it. Also, if you pull vacuums too fast, that moisture will freeze. You're not allowing enough time to pull a vacuum down to the proper microns. Even if it shows you the proper microns and it's frozen, that's a lie. It needs to be, you need to, let some pressures back in there, thaw it out, and then do like what they call a double or triple vac, which you're just repeating that same process until you continuously get back to 500 microns. My recommendation is to use a low CFM pump. If you have a high CFM vacuum pump, then just barely crack your gauge. You don't have to run everything wide open. Anything that's going to create a longer vacuum is good. Now, with that being said, dryers are very important. They're there to help mitigate this issue, and sometimes we don't find dryers in there. Sometimes dryers don't get replaced when we open up our refrigerant circuits. And so there's many reasons why you can have non-condensables, right? Somebody with bad practices can definitely contribute that or exacerbate that issue. When you have non-condensables, the reason why it's important to be removed, not only could it build up acid, right? Because there's no test to find out what is my non-condensable. Is it moisture? Is it air? If it's air, it's got moisture in it. Is it a different type of refrigerant? No matter how you want to compute that, what you should do, it's going to come out to the same practice. Remove it all and start all over again, but start it all over again with the right way. New dryer, proper evacuation, new virgin refrigerant, which means you didn't recover it, try to run it through a filter and put it back in there. No, it needs to be virgin right out of the bottle, or you're just not going to be able to fix that. Also, you're not going to ever be able to properly diagnose the system when there is issues, right? Because these values keep moving, and you need value. Values should not be moving around. They're moving around for a reason. Some people say, well, maybe my expansion valve is hunting. Okay, well, if your expansion valve is hunting, then you're not going to have an issue to where your subcool is going to drop, your superheat's going to drop, then your superheat's going to climb back up, and then your subcool is going to climb back up, and then they're both going to go up, they're both going to go down, and then they're just going to wind up doing their own thing. And the reason why they're doing their own thing that don't coincide with each other with one of these 3 things that it could be, top 3 things that it could be, is because we're condensing many things, we're evaporating many things, and it's in a sealed system that wasn't designed for it to be in there. And so we cannot trust the data that our gauges are giving us. When we see that, you just need to do the right thing and to start all over again. And sometimes it's just a simple startup procedure that went wrong. Anything, it can really be anything. So as frustrating as it may be, or as much of a great opportunity it may be for your company, when you experience that, it's best to do what's right for the customer, the client, and the product itself, and give it that reliability, that have some dignity in what you're doing, and do things to the proper trade practices and help mitigate that issue. I hope this video helps you out. Please like our channel if you haven't done so already. Share this with others if you think it's interesting and a good video to share out. I'm working on other videos in the future where I will be in the field to help just kind of change the channel up a little bit to where you're actually seeing me diagnose fresh problems just like this one. And my goal and my passion is to elevate people's confidence and knowledge within our industry. People that are working on this every day that go through these struggles. I've been doing this for, right now at this point in the video, 26 years, and I've had some very good people that have mentored me. I know what that's like when you finally have that person there wasn't a YouTube back then. I've also had people that are just envious and they don't want to see you get ahead because maybe you have good communication skills with customers and your soft sales skills allow your ticket average to produce results that employers like to brag about. And I've pretty much been on all ends of that spectrum, and you don't always get the best results from your peers that you're working with, right? That are there to really support you as one team. It's kind of like the quarterback doesn't want to throw you the ball type of thing. And at the end of the day, you are one team, and you're really there for the client, and that's what's most important. So you got to get through this. We are a culture. We are a band of brothers, and at the end of the day, uh, it is very unique to be in the HVAC industry. And so my level of understanding and commitment and knowledge and passion for it is here to help you utilizing this platform. And you can better help that by just sharing that, giving us a like, subscribing to our channel. That next video that comes out, it may be there to help you crush your service call. Thank you. Stay safe as always, and stay tuned.